And now it's time for Professor Susan Solomon to talk about ozone depletion from pole to pole and its linkages to climate change. Please.
Do we have this one up?
Very nice.
Yes, something to get it up. No, it's fine. Okay.
No, we need some.
We need to. There we go. Okay, wonderful. Well, thank you. It's a really singular pleasure and honor to stand before you today. I feel deeply, deeply humbled by this experience. I want to thank the Crafoord family and the Academy and all of my colleagues, the many colleagues who've contributed to the work that I'm going to be talking about today. I think it means a lot to the atmospheric chemistry community that our work is being honored in this way, and I feel tremendously privileged to represent that community. So what I'm going to try to do is to briefly summarize the history of ozone science. I'll talk a little bit about the physics and chemistry of the problem. I'll talk about the ozone hole when it opened, and I'll show you evidence that I'm very excited about, that we are beginning to see the emergence of closing. It won't close completely till about the middle of the century, but it is observable that it is improving. I'll talk a little bit about the international agreement and the recent paper in Nature that talks about a leakage or an unexpected emission that you might have heard about this past week. And finally, I'll talk about the effect of the ozone hole on surface climate of the southern hemisphere. Our interest in ozone stems from the fact that it is the shield for life on the planet's surface. If we had no ozone layer, we wouldn't be able to survive because ultraviolet light is very damaging to DNA of not only human beings, but also animals. And I'll talk about several wavelength ranges in the spectrum, not just ozone's absorption in the UV, but also absorption in the visible and millimeter waves that we actually use as remote sensing methods to probe the chemistry of the Antarctic atmosphere. Well, it's not hard to convince people that ozone depletion would be a very bad thing for life on Earth. This, of course, is a very somewhat humorous picture, but you can imagine how much that gentleman will hurt later. And of course, if you get sunburned too many times, it can lead to skin cancer, which is a very serious thing indeed. It can also lead to cataracts. Again, another very serious issue. So it's protecting us in a way that I think you could describe as deeply personal to human beings. And I think that's one of the reasons that it attracted so much public attention when the Antarctic ozone hole was discovered. But I want to step back in time to before the discovery of the ozone hole. In the mid-1970s, Mario Molina and Sherry Rowland published this landmark paper in Nature, where they pointed out that chlorofluorocarbons that were being used in ever-increasing amounts had very long lifetimes. Depending on the molecule, they live anywhere between 50 and 500 years. And they said that material has nowhere else to go but up into the stratosphere, where the chlorofluorocarbons break down, make chlorine atoms, which can react with ozone to make chlorine monoxide. And remember that molecule because it's very critical in this cycle that I'm showing you. That guy goes on to react with atomic oxygen, making chlorine atoms back again, and this guy can go right back up here and do it again and again and again, which means it's catalytic. You only need a tiny amount of chlorine to destroy a lot of ozone. And so I also want to point out that for the students in the audience, it's really important to proofread your papers because you never know when you're going to make a typographical error, and it would be such a shame to get a Nobel Prize for a paper that had such a little mistake in it, but I think it's kind of cute, actually. I want to emphasize that Rowland and Molina shared the Nobel Prize in 1995 with Paul Crutzen, and I had the great honor to be Paul Crutzen's graduate student. So it's a singular pleasure for me to be standing here before you today, and I owe all of that to Professor Crutzen. So, This work that Melina and Roland did considered only gas phase molecules. Every reaction I've talked about is happening in the gas phase. And I'll come back to that in a minute. Based on that sort of chemistry, by 1983 or so, we expected that if we kept using chlorofluorocarbons in the kind of amounts that we were doing at that time, that we might see a 5 to 10% depletion in the ozone layer in 100 years. So a small effect, far in the future, hadn't yet been observed, it was only a theory. And of course, the main use, 75% actually of the global use at that time, was in spray cans. It was the propellant that got material out the nozzle. Everything from paints to, of course, hairspray was a very important use. Also deodorant. So interestingly enough, most of the use was occurring for those kinds of what they called personal care products. But in 1985, everything changed, because that was the year that the British Antarctic Survey announced their discovery of an ozone hole in the Antarctic. They weren't seeing 5 to 10% in a century. They were seeing about half of the ozone going away at that time in the 1980s, and in a place where no one ever expected to see any special sensitivity. No one said Antarctica would be special. So it was a shock to the scientific community, and I was very lucky to be a young scientist at that time and have a chance to really build my career on this problem. So I'm going to tell you a little bit about that. First, I want to just honor them a little bit more. So Joe Farman and his colleagues were the guys who had this record. And when they saw the October averages just taking this incredible nosedive at their station here at Halley, which is right there, they told the world about it, and now here's the rest of the record. So it still has fluctuations from year to year, but you can see that it's much, much less than it was historically. The wonderful satellite images, of course, that we're all familiar with were great for people understanding the problem, and the Japanese station quickly confirmed the British measurements, as did the American station at the South Pole. So the bottom line was that you had a very graphic image. It was easy to understand. People get interested in the Antarctic, and unlike the climate change problem, you don't have to be a statistician to really see. I mean, this kind of change is pretty obvious. So it was a very readily accessible, perceptible problem as far as the public was concerned. Now I'm going to just quickly show you a film clip of last year's ozone hole. So in July, you don't have much of a hole. You don't have much less ozone in Antarctica than you do anywhere else. But as you get into August, you begin to see these levels of ozone get lower and lower. And by the time you get into the beginning of October, you've essentially destroyed all the ozone at certain altitudes in the heart of the layer, as I'll show you. And then as the stratosphere warms up, that ozone hole dissipates. So it forms during the cold period, but it also needs sunlight, and I'm going to tell you why that is in just a few minutes. So wintertime sort of sets up the ozone hole, but it's the return of sunlight in the spring that kicks it off. I was very fortunate to work, particularly I want to acknowledge the work I did with Rolando Garcia over many years, and this paper that appeared in Nature in 1986, a bit more than 30 years ago, is where we pointed out that the key reaction that might be driving this is not a gas phase reaction, but rather a surface reaction. So what happens in Antarctica is it really is the coldest place on Earth. It's so cold that these beautiful polar stratospheric clouds form, and they allow this molecule, hydrochloric acid, which is a stable molecule on its own. It doesn't do anything to ozone. It's come from the chlorofluorocarbons. When they broke down, they made hydrochloric acid. But that guy reacts with chlorine nitrate on the surfaces of these clouds to make molecular chlorine and nitric acid. Molecular chlorine, in turn, is very unstable. As soon as the sunlight comes back, it breaks up, makes chlorine atoms again, and I'll show you that in more detail in just a second. But the key point is that the man-made chlorine is key. This wouldn't happen if we hadn't increased the chlorine. It's not the clouds themselves, in a sense, that are causing the ozone hole. It's the fact that the chlorine has increased by about a factor of 5 compared to the natural levels of chlorine in our stratosphere. And they team up with this extreme unusual circumstance in the Antarctic to produce ozone loss as soon as the sun comes back. So it's surface chemistry that's driving this, not just the gas phase chemistry. We don't see depletion like this in the Arctic, and I'll show you that. We do see certainly quite some depletion. There is ozone depletion in the Arctic that's much more than at mid-latitudes, but it's not nearly as much as the Antarctic, and I'll show you that. So the way that this works is those two molecules are reservoirs as far as chlorine is concerned. When they react together on the surfaces of these clouds, they make molecular chlorine, photolyzes, making chlorine atoms, and now you've activated the chlorine. I'm not going to show you the rest of the chemical reactions that go on after this, but at that point you're driving some very important catalytic cycles that can deplete the ozone very effectively. And it does it at a different height range than the gas phase chemistry does. This is a typical ozone layer. So the ozone is mostly between about 10 and 30 kilometers. We're well above our heads in the stratosphere. Not much ozone down here in the lower atmosphere. Of course, it can get increased by smog and things down at the ground. I'm not talking about that at all today. I'm only talking about stratospheric ozone. The gas phase chemistry that Moline and Rowland discovered would destroy ozone way up here at 40 kilometers, but there's not much ozone there. So that's why you only get 5 to 10% change in the integrated total amount between you and the sun, which is your UV shield. The polar stratospheric cloud chemistry, on the other hand, allows you to really hit the heart of the layer and take it essentially completely out. And now I'm going to show you that. To do that, you need cold temperatures and you need sunlight. So I just thought it would be fun to show a few pictures of going to Antarctica. That's myself on the tarmac in New Zealand, getting ready to go down to Antarctica as part of the National Ozone Expedition. It's August, so it's the end of the winter, beginning of the spring down in the southern hemisphere. We take off at 3 o'clock in the morning because it's a 9-hour flight to get to Antarctica, and the pilot would like to be able to kind of see the runway in the twilight that happens to be present at noon. So the sun's not yet getting up above the horizon. We get there just in time to start making the measurements of the ozone dropping. And that again is myself arriving in Antarctica, and it was about minus 40 degrees Fahrenheit, which, by the way, is also minus 40 Celsius, the only temperature at which they are the same. And it was just the most incredible experience in my life to be on that expedition, together with some of the finest colleagues that anyone could ever ask for. I was the only woman on the expedition, and I was also nominally the leader of the expedition with 16 people. And honestly, every single one of those 15 people, colleagues, were incredible, never did anything but help and support me as the leader of the expedition, and I'm so grateful. So one of the people that was leading one of the subgroups was Dave Hoffman, his colleagues, and he launched ozone measuring balloons. So they put electrochemical instruments on board these wonderful balloons, and they would rise up into the stratosphere and get measurements that looks like this. So if you take such a measurement in August, you get the blue line, normal ozone layer, but by the time middle of September rolls around, you start seeing these bites taken out of it where the polar stratospheric clouds have been active. By the end of September, you've destroyed quite a bit of the ozone. By the beginning of October nowadays, it essentially gets driven to zero. That actually didn't happen back in the mid-'80s when we first started doing it, but now it has often been like that in around the period, especially around the year 2000. It's actually getting to the point where that doesn't happen anymore, and that's another interesting question. But what basically is going on then is that from 10 to 25 kilometers, the ozone is completely wiped out, and that's exactly where the polar stratospheric clouds reside. So it's a very important fingerprint in altitude that points towards the clouds as the driver of this in some way. But knowing that that's where it's missing doesn't really tell you that chemistry is driving it. For that, you need to turn to chemical measurements. And in my own group, particularly together with Ryan Sanders and George Mount, we did visible spectroscopy. So what that means is we're collecting moonlight, sunlight, twilight even, actually, and we direct those photons with a mirror that I think I'm adjusting right here down into the instrument, and we basically use a spectrograph, which just like a prism divides the light up, the white light, into different colors. And since there are certain wavelengths where different chemicals absorb, if we measure the absorption of the incoming sunlight as a function of color or wavelength, we end up with something that looks like this, where this dashed line is what chlorine dioxide, a close cousin of chlorine monoxide, would look like as a function of wavelength in the blue part of the spectrum, actually. And you can see how great a match it is to what we actually observed using moonlight in the Antarctic. So it's a wonderful spectral fingerprint of the chemistry. And what that tells you is we shouldn't have been able actually to see anywhere near this much chlorine dioxide if the clouds weren't causing that incredible perturbation of the chemistry. It's about 100 times more than there should have been for, if you will, standard chemistry. Another technique that was used, and I just for this audience want to spend a few minutes talking about it, millimeter wave spectroscopy is a very elegant technique for probing CLO. It's now also done from satellites by the group from JPL. So if you're looking at, in the millimeter wavelength, you're actually looking at the emission from a single rotational line of the molecule in question. CLO has a nice feature they can look at. If it's broad like this, then the CLO is relatively low in the stratosphere. If it's narrow, the CLO is high up. So for the gas, because those lines are pressure broadened. If it's gas phase chemistry, you would expect to only see this. If it's low down, you would expect to see that. So low where the polar stratospheric clouds reside. And that's what de Zafra and his colleague Phil Solomon and others, Phil's no relation to me, I should add, did. And what they got was something looks like this, and you can kind of see it's got that broad thing, but it also has that little narrow thing. You can invert that and see the CLO that the Molina-Rowland theory would give you. And you can also see this huge layer, which shouldn't be there. It should be essentially zero, except for the role of the polar stratospheric clouds. So this was a wonderful direct measurement that was really, I think, pioneering in showing that the chlorine was the cause of the ozone hole. This just should not have been there at all without clouds and without chlorine. So there's the fingerprint of the gas phase chemistry and the fingerprint of the heterogeneous chemistry. Fingerprint in altitude, another one. Also a fingerprint in latitude that I would be remiss if I didn't mention the work of Jim Anderson and colleagues from Harvard, as NASA actually organized an aircraft mission which flew from Punta Arenas down to Antarctica and back. And as they did that, here's the very, very low levels of CLO that you see flying out of Punta Arenas. And then as you cross into the Antarctic, you see this huge surge in CLO, and this drop in ozone is coincident with that. So that fingerprint in latitude, some people referred to as a smoking gun. It was a very, very compelling and useful way to talk about this to the public. Within a few years then, with several independent techniques, visible spectroscopy, millimeter spectroscopy, airborne resonance fluorescence, also, we measured hydrochloric acid using an infrared technique and were able to show that it was very, very low when the CLO was high. All the pieces of this wonderful chemical puzzle fit together, and we were able to show that there were massive perturbations happening on Antarctic polar stratospheric clouds involving chlorine, and that was what was certainly capable of depleting the ozone layer there as it was. What a wonderful, wonderful thing for a young scientist to be part of. I was only 30 years old at the time. Well, we got lucky in a way because in the early days, we initially, I think, at least I imagined, that the clouds were ice. They are ice when you see them like this. These beautiful pictures only come from the ice clouds. So some of them definitely are ice. And laboratory chemistry by many people, I want to mention particularly Maggie Tolbert, showed that the ice surfaces were very reactive, that hydrochloric acid chlorine nitrate reaction that I mentioned could indeed happen very, very rapidly on an ice surface. So 1 in every 10 collisions or so, maybe even 1 in every 3, when a chlorine monoxide molecule hits an ice surface, it finds an HCl and reacts. But you get comparable numbers actually for other kinds of surfaces, and we now know that those other kinds of surfaces are also present. So let me just say a little bit about how polar stratospheric clouds are formed. They're both in frozen form and in liquid form. They start out as liquid sulfuric acid and water small particles, aerosols. They can freeze. They can make nitric acid trihydrates, which also have a significant reactivity towards chlorine, but they need not freeze. Sometimes they supercool, and they make liquid polar stratospheric clouds. I should here mention the work of Karslaw, Peter, and Tabazadeh, and Koop, all of whom have made tremendous contributions to this. Toon and Arnold and Crutzen made tremendous contributions to understanding the nitric acid trihydrates. Ravi Shankara studied all of them, actually. So based on these wonderful laboratory and modeling efforts, we now understand the fact that the particles can be liquid. They could also be ice or nitric acid ices. And it turns out that it actually doesn't matter that much for the chemistry, amazingly. And the reason is pretty simple. There's been a lot of advances in studying ice surfaces, particularly using low-energy electron diffraction methods. And what you find is that the ice surface remains disordered on the surface. So you have order in the center, but you often have a quasi-liquid layer on any kind of ice. And even on ice polar stratospheric clouds, you have that down to quite cold temperatures. So in this quasi-liquid layer, the ice is reacting very much as a liquid would. And so for temperatures below 192 degrees Kelvin, if you have sunlight, whether the particles are liquid or solid, you get fast reactions. And it just doesn't matter that much what the particles are made of, because the reactions are so fast that they effectively activate all the chlorine. If you can activate all the chlorine in 10 minutes, it doesn't matter if it's going to take 20 minutes. That's basically what it boils down to. I want to acknowledge the very important work done here in Europe. I've talked a lot about some of the US measurements, but European scientists have been leaders in understanding the differences between the Antarctic and the Arctic. Not surprisingly, we went to the Antarctic, and more Europeans looked to the Arctic. The balloon site in Kiruna, Sweden, is a very important resource for atmospheric science and atmospheric chemistry. And campaigns that were involving people from all around Europe were very important in looking at Arctic versus Antarctic ozone. So let me say a little bit more about that. Again, here's what the Antarctic looks like. There's normal ozone in the 60s and 70s from South Pole, and this is later periods. You can see the sort of picture I showed you before. This is the kind of thing you get in the Arctic, rather different. You certainly see some depletion in places like Finland, and in really extreme years, it's pretty significant. I'm going to show you that in a little more detail in a second, but you can see that it's really nothing like what you see in the Antarctic. So the simple reason, the Arctic is warmer and just doesn't drive the chemistry as hard. So to show you that, I'm going to take a slice now, right here, right kind of at the top side of where the depletion happens. And in Antarctica, we're going to get down to very close to zero. And the Arctic, as you'll see, doesn't happen. So let's take a look at the Arctic and the Antarctic. Here I'm showing you the Antarctic in September. You can see what the temperatures do at that level that I talked about, and you can see what happens to the ozone. In the old days, and this is a log scale. I'll take the mystery away. I'll let you see the Arctic at the same time. I was going to do it slowly, but you can see that it's a log scale, and that basically, in the old days, this is the historic data from the 60s and 70s, ozone hardly changed as you went through that spring season. So this is day of year, the sun's coming up around here, and this is where the ozone begins to be destroyed. You lose not just a factor of 10, not just a factor of 100. Sometimes you actually lose more than that. So, you're down to less than 1% of the normal amount of ozone happening in the Antarctic. And it happens as the temperatures remain cold, but the sunlight comes back. The Arctic is just warm enough not to do that. So what you see here is, yeah, you're getting some very serious depletion, but you never see the values like these. And the reason, here's the various stations. All of the different stations are represented on these plots. Some of them are very close to Sweden. Let's just take a look at the temperatures The difference between the coldest temperature and the Arctic at that level is, maybe minus 84 degrees Celsius, whereas over here it's more like in the minus 90s. So it's those extra few degrees that make all the difference, and it's that extra measure of stability of the Antarctic vortex that does that. Well, as you know, the nations of the world agreed to a really landmark international agreement in 1987. They said they were going to freeze and then phase out the chlorofluorocarbon emissions. So the initial protocol, chlorine in the atmosphere would have done something like this. It would have been really catastrophic for this planet if they'd never done anything more than the initial protocol. But that's not what they did. What they did instead was to decide to phase it out in developed countries first, and then in developing countries. And now we're following pretty close to the zero emission line, which means that if you ask yourself how long you're going to have to wait to have the ozone hole recover, it's something like 2050, 2060 that you're going to get back to the levels of chlorine that we had in 1980 when it first became obvious that there was an ozone hole. So the chlorofluorocarbons with their long lifetimes take that long to get out of the atmosphere. Well, most people would have said, how on earth did this happen? It's kind of, when you read the statements that were made about the negotiations, you think you're reading about climate change negotiations, because they had really a lot of the same elements in the beginning, but that's a book about the ozone negotiations by someone who was actually the head negotiator for the United States, wrote a wonderful book about it. I want to talk a little bit more then about how this happened from a societal point of view. Why did we get the Montreal Protocol in 1987? Well, it's not because the ozone hole appeared. That was in 85. Oh, I forgot to introduce this for you. I apologize. What I'm showing you here are the metric tons of chlorofluorocarbons sold as a function of year. So this is just how much CFCs the different chemical companies are making and selling in the United States and the rest of the world, and the total. And you see this drop in the United States somewhere around 1974 or so, 1975. The rest of the world, interestingly enough, stayed, didn't actually drop, and I'm going to talk about that in just a second. But the protocol, why did this drop happen? The protocol wasn't signed till 87. The ozone hole wasn't discovered till 85. It was that theory, the Molina-Rowland theory of possible ozone depletion in the early 70s, and I have to say also the work on catalytic chemistry that Paul Crutzen did was also pivotal in a lot of this understanding. It was that led people to turn away from the chlorofluorocarbons in the US. And honestly, they did that because it wasn't that hard to do, right? I mean, what you had to do was go to your medicine cabinet and take this and replace it with that. Now, how hard is that? Would you do that if somebody asked you to? Of course you would. It's the sort of thing that made sense, and it was easy to do, and people engaged, just as they do today with recycling, as they're beginning to do with things like use of plastics. People, I think, will do things when they see practical solutions. And what that did for the United States was turn good business into bad business. I'm proud of the fact that in the 70s, the United States was a very environmentally conscious country, and people, consumers, made this choice. We didn't actually ban the chlorofluorocarbons in spray cans until 1978, and I'll say more about that in a second. In the rest of the world, most of the other countries, with a few exceptions including Sweden, didn't stop using chlorofluorocarbons. In fact, most of continental Europe kept using them well into the 1990s, and we have a burden of chlorofluorocarbon in the atmosphere today as a legacy of that is really kind of sad, because it really didn't need to happen. This was not that hard to change. So I'm moved by the fact that the Montreal Protocol was due to the action of consumers, but I want to emphasize not just US consumers. Sweden actually was the first country in the world to announce a ban on CFCs and spray cans. You did that about 10 months before we did it in the US. Norway, Canada, and I believe Japan also did that very early. And other countries followed suit over time. So is the Montreal Protocol working? We always get this question. The answer is yes, of course it is. Here's the chlorofluorocarbon 11 amount in the atmosphere as a function of time. And we have measurements from many places around the world, which allows us to look at the northern hemisphere versus the southern hemisphere. We can see this dramatic rise in chlorofluorocarbon 11 going on through the 80s and into the 90s until the Montreal Protocol began to reduce emission. And so you can see the amounts starting to drop. It'll take a long time to drop because of the long lifetime. But the other thing that should have happened by now is that the southern hemisphere and the northern hemisphere should have been pretty much closer to having converged. So the reason for that is, the reason the northern hemisphere is ahead is because most people live in the northern hemisphere, so most of the production and emission is happening there. It takes a while for that air to get mixed down to the southern hemisphere, but eventually it gets there. It's only a few-year lag. But if the source stops completely, the two hemispheres should converge. And that's not only not happening, but you kind of see it almost looks like it's getting bigger, that difference in recent years. That's what that paper in Nature last week was all about, and I don't have time to go into all of it. I just want to say that, indeed, we have seen this drop, so the protocol is working, but it's not working perfectly because it should have dropped more. The number one line here would have said we should be around here, and instead we're up here. So there's a significant source of chlorofluorocarbon 11 out there. It's nowhere near as big as it used to be in the 90s and 80s, but it is significant. And we're not sure where it's coming from. Fascinating problem, and very illustrative, really, of the importance of having all of these stations. Because we have such a distribution of stations, we know it's coming from somewhere in Asia, but we don't know where. And I don't think we should point any fingers. It's not necessarily rogue production. It could be, but personally, I sort of doubt that. I think it's possibly due to the fact that we've underestimated how much chlorofluorocarbon is out there in what we call the banks of materials. So the banks are in things like refrigerators, air conditioners, chillers, supermarket, freezers and things like that. There's a massive amount that's already in installed equipment, also actually in the foam, insulating foam of many buildings. They used to actually use chlorofluorocarbon for that, can you believe it? And that stuff, of course, is continuing to leak out. Here in Sweden, and actually also in Japan, people have done an excellent job at recovering and destroying the banks, but other countries haven't done quite so well. In my own country, we haven't done well at all. And I think understanding the magnitude of the banks is a serious challenge, and I'm actually working on that right at the moment, thanks to a project that I have on that. But another thing that it could be is just an accidental byproduct of making something else. The chlorofluorocarbons are feedstocks for making other things like plastics. It's possible that it's just leaking by, accident from, not a deliberate production, but just not careful enough control of feedstock chemicals. And I think it's not going to be very long before we'll know what's going on, and we can thank those wonderful global measurements for knowing that it happened at all. So I want to say a little bit about the fact that we do see improvement already in the ozone hole, and it's just exactly coincident with what we would expect to see if you look at it the right way. I, together with a number of colleagues, particularly Doug Kinnison, I'd like to acknowledge here, and Diane Ivey, we published a paper in Science in 2016, and what it did was to take a look at the evolution of the ozone hole, not just in October. I think we were all fixated on October because that's the month in which the British Antarctic Survey used their measurements, showed the ozone hole in October. And October is the month of the greatest depletion. It's not the right time to look if you want to see the beginnings of the healing of the ozone hole for reasons that I'm going to explain now. So if you take a look at the growth of the hole in terms of area, millions of square kilometers, the hole typically gets to a maximum size of about 20 or 25 million square kilometers. It's an enormous hole. The observations and a very good computer model, this is the NCAR chemistry climate model, driven by observed temperatures from reanalysis, so the temperatures are accurate. If you look at this, you can see that it does a pretty good job of simulating that seasonal evolution. That's what it used to do in the 90s and into the aughts, and that's what it's doing more recently. So you still get to pretty much the same kinds of levels if you wait until October, and maybe it's a little bit lower, but it's going to depend on year-to-year variability. A little colder year, as I showed you, temperature is very important, so slight changes in temperature make a difference out here. But what's sort of inexorable is that if you have less chlorine, it will take longer for the ozone hole to develop, to get big. That's just basic kinetics. So the rate at which a chemical reaction is driven depends on the amount of reactant. September, which is days 240 to 270, is a period when there's not much variability, and when, so there's not much, up and down from year to year, and that's the time when it's forming. So you want to look then rather than later on, because later on, if it's been driven to zero, like I showed you, it may still be very close to zero anyhow in the heart of the ozone hole, and you won't see the difference, and I'll show you that more in just a second. Even in years with major volcanic eruptions, you still see this lag. So you still see that in recent years, it's taking longer for that ozone hole to open up. Another quick look at how you can look at this, you can go to the halfway point, about 12 million square kilometers, and you can ask yourself how that's varied. What day of the year did it take to see 12 million square kilometer ozone hole? And you can see how it got earlier and earlier and earlier. First, it wasn't happening at all, of course, because there was no ozone hole. And now it's really taken this nosedive to about the year 2000, when it's happening in late August. And you can see how even in the coldest years, it takes longer for it to reach its 12 million square kilometer mark. So so this was, I must say, very moving to me. We published this paper in 2016. In 1986, we published the paper talking about the chemistry. In 1987, we went down there and confirmed the chemistry, and frankly, to 30 years later be standing before you saying that the world has done the right thing and put the ozone on the path to healing is a tremendous, tremendous feeling. So this is just a simple box model to illustrate the point I'm trying to make about October versus September. By October 1st, regardless of how much chlorine you have, the maximum level, a little less chlorine, a lot less chlorine, you can still get to the point where you essentially have zero through the whole month of October, and that's what's happening. But the rate at which you get there varies very strongly with how much chlorine you have, and that's why September is the key time to look. Plus, it's less variable. I'm going to skip this in the interest of time. I do want to just touch on the linkages to climate. This was something that I have done a lot of work on with my colleague Dave Thompson, and it's been another tremendous thing I think for our field to really recognize that what's going on in the stratosphere can actually affect the surface. So here's a little bit about how that works. Because ozone absorbs ultraviolet light and keeps you from getting sunburned, it actually heats the stratosphere. That's where the energy goes. Ozone is the primary source of heat to the stratosphere. So if you drive it down to zero, what you're going to see is the stratosphere won't heat as much. It'll get colder. And indeed, stations all around Antarctica, this very nice analysis by Randall and Wu, and it was actually Keith Shine, I think, that first really talked about this. As you decrease the ozone, you make the temperatures in the ozone hole region some 10 to even more degrees colder than they would otherwise be, 10 Celsius. So it's a massive change. The stratosphere gets much, much colder. How does that affect climate? I want to just emphasize, ozone loss is not the cause of global warming. The primary cause of global warming is carbon dioxide increases, which Professor Manabe summarized so beautifully. But the ozone hole changes the circulation and the wind pattern in the southern hemisphere, and through that actually influences surface climate. So as the stratosphere gets colder, the polar vortex, which we're all familiar with, you see the vortex wobbling over places like North America or Sweden, that's when we get cold. If it stays bottled up over the Arctic, we are relatively warm. So when the vortex gets colder and tighter and more symmetric, then the region on the high plateau cools. And that's exactly what we've seen in the period from about 1970 to the year 2000. So basically, the vortex in the Antarctic has gotten less wavy. It's not very wavy to begin with, but it's gotten even less wavy because what happens in the stratosphere can propagate all the way down to the ground about a month later. And Professor Thompson's going to talk about the mechanisms for that I think. When you make it colder here, you actually also make it warmer on the peninsula region. So you're just not getting that Antarctic air coming out over the Antarctic peninsula the way it used to. And that has had a big effect on things like glaciers in the peninsula. But it's also reaching all the way over to South America. And you can see how it's affected the winds. The jet stream has moved over, so moved more poleward, and it's gotten stronger. And so the wind system is getting shifted. That shift in winds actually also affects surface temperature extremes. And in the last couple of minutes, I just want to say a few words about that. We did a study with my graduate student Bandoro as the lead at MIT, looking at the pre-ozone hole era and the ozone hole era. And you can separate it out into years with high ozone, years without as much ozone loss, and years with low ozone. So find the anomalously low or anomalously high years. And you even have some in the ozone hole era. It's all relative to a new background, but you can still find them. You can take out the mean, any trends in temperature, and then you can take a look at, and you can also take out El Nino. I don't have time to talk about all the details of how we did that. But what you can do is take a look at how maximum daily summer temperatures have changed. And it's really quite remarkable. In the ozone high years and the ozone low years, in the 50s, 60s, 70s, 80s, early 80s, they were essentially the same in this spot in Australia. But as you get into the period of the ozone hole, the ozone high years are warmer than the ozone low years. Same thing is true in Argentina, for example. So these extreme high temperatures happen more often when ozone is high. I don't have time to talk about all the reasons for that, but it has to do really with that shift in circulation, and accompanying changes in rainfall are actually also important. In Africa, you see it too. We don't have as good of early measurements, but you can also see this shift. So what it means is that the low ozone years, those are the years with the cooler extremes. So ozone has sort of held back global warming in these places, right? So the ozone loss, the depletion, the formation of the hole has kept global warming from being as bad as it's going to get as the hole continues to heal. So Australia, which has had so many problems with fires, South Africa, which is having so many serious water problems, all of that is going to get even worse as the ozone hole recovers. And that's, to me, kind of scary, but that's the consequence of that change in circulation, which affects rainfall. It's mainly why it's happening in these dry regions. And again, I don't have time to go through the details. So these are the points that I think we've touched upon. I think we should all celebrate, in particular as a planet, this one, which we all contributed to. And thank you very much for your attention and for this honor. Do we have time?
Oh, excellent timing. Thank you, Professor Solomon. So do we have any questions? It was a truly fascinating talk. Yes, we have several there. Början?
Thank you for your heroic work and for a great presentation. On the link between the stratospheric ozone depletion and current climate change, with the phase-out of CFCs, HCFCs, and HFCs, and so on, I understand that methyl halides are becoming an increasingly important component in these processes. And in analogy to methane, where there are large uncertainties, but there are predictions of possibly increasing emissions from tropical wetlands and coastal thawing permafrost in the Arctic, these methyl halides have both anthropogenic and natural sources. In your mind, what is the possibility that increasing methyl halide emissions due to climate warming might slow down the recovery of the stratospheric?
Yeah, that's a great question. One of the things that maybe is worth thinking about is the decay of the chlorofluorocarbons is so slow that even relatively small sources that we didn't think about so much before can actually get important because you're kind of like the frog trying to approach the log, you know. If you get a little bit of something happening, it can slow it down because it's competing with a slow removal rather than a fast increase. So I don't think, and so you've mentioned the methyl halides. Methyl chloride is the main one, and its natural sources plus anthropogenic sources are relatively small compared to the current burden of chlorofluorocarbons. It would have to increase enormously to get to the point where, you know, it would cause the ozone hole never to go away. That's just very, very unlikely. Could an increase in emissions of methyl chloride from human activities, from biomass burning, I think you're thinking about maybe the temperature of the ocean, all those things could indeed increase those small sources enough to slow down that slow recovery. Another thing that's been mentioned in a very nice recent paper by Hosseini and Chipperfield is the dichloromethane, which is used as I believe, as a paint stripper. It's not been controlled under the Montreal Protocol, but the emissions of it are growing, and it's like everything else, you know, with so many people on this planet using lots of stuff. If we don't pay careful attention, you know, we might be surprised. The amount of dichloromethane is very surprising. And again, it's not enough to stop the ozone hole from recovering, but it's got the potential to slow it down by a few years. So it's all the more reason we should read the labels of our products very carefully, but we should also continue to study these much more challenging potential feedbacks like the one you mentioned, methyl chloride and other short-lived compounds. Short-lived bromocarbons also, actually.
I think we managed one question more.
Oh, it's a quick question, actually. You said that the CFCs are long-lived, and I'm wondering how long-lived are they? How long can they be up there?
Yeah, it depends on which one, which is why I didn't give you a single number. Chlorofluorocarbon 11 is about 50 years. Chlorofluorocarbon 12 is about 100 years. Methylchloroform is only about 6 years. So, you know, it's a mix of lifetimes, and it's the mix of the chemicals. Chlorofluorocarbon 115 is 500 years. So, you know, some of them are going to be around for a long, long time. But some of them go away relatively quickly. And what we're seeing now are the ones that have gone away relatively quickly, obviously, the recovery that we've got so far.
And are these different CFCs stronger than like they can differ in how strong they are when it comes to depleting the ozone layer? Or?
Yes, and we take that into account, of course. I mean, we know exactly those numbers. Thanks to laboratory chemistry, we understand very well the processes that deplete those things, that destroy those molecules, how long they take. How many chlorines how many chlorine atoms are in the molecule is, you know, not hard to know. So we have all that information. Is that too long an answer for one more?
Perfect.
Okay.
So I think we give Susan one more applause.